There's Fisherman. Fire kitchen. I don't even know what fire kitchen is. Now I need to, though. Alright. I normally give people a couple minutes to show up, but it's Saturday night, and I don't normally stream Saturday night, so I don't know when the wife's getting home. She's hanging out with one of the nieces for a bit. They were going and doing very girly things that I was not interested in doing. So I'm just hanging out here with Ranger. 24/7 greatest stream. That's funny. Okay, let's throw over some stream goals. I'll probably start popping these up again. I used to do these a long time ago. I would always have the stream goals like down in one of the corners of the stream, and I kind of got away from it. Ranger check. Let's go check on Ranger Dog real quick. Pop this up. We'll go pop over here. We'll get the old Ranger cam going. Oh man, I gotta sign in and everything. Hold on. That should be Nagios admin and Nagios. Wait a minute, what happened over here? Hold on. Get over here. Ah, there I go. Now I can see anything. Hold on. Is that Nagios admin? I think. And that one's maybe that. There's Ranger. By the way, Ranger's been a little bit slow getting up the last week or so. We got him on a bunch of drugs now from, on last Sunday, he went on an emergency vet. And then just Friday, he went on his regular vet. And, man, I mean, it's not like an acute sudden onset of being old, I don't think. But he's having problems. And they think if he doesn't get better in 5 days on all the pills and stuff they got him on, they're going to do x-rays because they think he hurt his back. So, oh man. Told Ranger, I'll just do it real quick with a garrote. No, I wouldn't do that. Can't tell my wife that anyways. Alright, anyways, so what are we doing today? That was Ranger check, so Ranger check's good. We're going to do some system stuff. Oh, I'm not even all connected. Hold on, let me connect up here real quick. Get on some of my stuff here. Hopefully that didn't drop anything here. Shouldn't have. Let's jump on this guy. Let's get on this box. So this will be a server that we'll use to kind of do some testing in general, looking at system stuff as we go through this. But this is the HPC System Engineering topic talk that I gave earlier to our prologue. And I know people wanted to see channel redeemed for upgrade one home lab. Fisherman, I used to have that. And, you might be surprised, but I think I had that. Wait, can I not see my channel points? Hold on. Stop. Oh, it's 8,000, but maybe I got rid of it. Maybe I got rid of that one. It says it's 8,000 on there. But here's what we used to have in the home lab. Wait, hold on. What was this called? It was name of that board where you put the sticky notes up. Hold on. Oh, what the heck is the name of that board? You guys, I'm drawing a complete blank here. Not a Cabana board. fuck is the name of that board where you put the messages? It's like an old project management Kanban. Yeah, so I got lab cleanup on Kanban. I don't know if you ever saw this, Fisherman, but what? I don't remember how to get in here. Maybe that. Maybe that. Oh yeah. Yeah. I have all kinds of stuff I need to do in the lab. I just don't do it. Yeah. I got this one, and then I got the home version of this. So there's like there's the lab cleanup and the home projects. So lab cleanup's all this stuff. The home projects are all these things I got to do around the house eventually. Or things that I've done. Some things I've done on the far right. Anyways, AWX upgrade. Oh yeah, I've been meaning to do it for a long time. Oh yeah, you guys have been telling me to do shit for a long time on this channel. I haven't been doing it. Yeah, so I can upgrade AWX. What I need to do for AWX is like this. Let's just get in our box here. So I gotta do something that, let's get this all connected up, just so we got it. We'll put it here. So it's on the other side of this. And what I need to do, to fix that up is I've got my production, heck, I leave it on a thing, and then I find, oops. There we go. So all I need to do is come in here and just set this all up. So that's all I really need to do, and then I would just decom the old one, because I think my version's on version 9 right now, and that's all I got to do to get the AWX going. I haven't done it yet. Yeah, if you fix a lab item, yeah, Fisherman, we can do that. That's not what I was going to do tonight, but I was hoping to just mess around tonight. Talk about this HPC type stuff, but I got to rebuild Jumpo 1. Man, I got so much crap to do on here. Pulp install, telegraph. Pi-hole. People wanted me to set up Pi-hole, play with Tmux. Oh, daily pull of all the IP data using Python and Folium. I've done all that before. I just need to show how to do all that. Yeah, Fisherman, I haven't looked at this in a while. My son always makes fun of me because not surprisingly, I have a bunch of hardware errors on the front of all my servers too. So I got to do that. Red, we were going to do red a long time ago. Duplicati, some people asked me to do. Yeah, these are from like years, like, how long ago did I write some of these? Yeah, 21. Is that almost 2 years ago now? Like, some of this shit's really old. But this is a pretty cool little tool. When you set this con board up, it's as simple as just dropping it in var www.html. It's actually pretty simple as far as all that stuff goes. And then you just set up some security stuff. I did set up the Kubernetes lab with Kafka, so that's all done. All right. Yeah, I'll get around to it, I'm sure. Of course. All right. So here's, for people who got here late, here's what we're doing. This is our topic. Learn about HPC and how to get skills in that area of engineering. So if you guys were around for the Professional Linux Users group today, you already saw some of this. And we'll just go through this a little bit. I know nothing about him, Inspector. Nothing relevant, anyways. Nothing useful. But this is the HPC Engineering Topics talk that I gave to the Linux Engineering group earlier. So if any of you guys want to follow along and do it with me, hang out, talk shop, ask questions if you've got them. I will tell you if I don't know, but I've been in the HPC space for the last 14 years, give or take, 15 years almost. And I've been doing Linux for about 20, so professionally. So, you know, let me know if you guys have questions or you want to work through any of this. But let's go through it. So here's kind of the overview. What is HPC? How is it used? What industries and applications are you going to find it in if you're trying to get it? Professionally, yeah. In that people paid me to do it or to not do it in some cases on their systems. System skills. These are generic Linux skills. Like pretty much everybody that probably watches my channel, for sure everybody down in the professional Linux users group, are people who have some basic Linux skills. But maybe we're a little rough around the edges, maybe we're hobbyists and we need to learn it a little better. So this is my idea of like what I think you need to bring to the table and things that you kind of need to know to be able to do HPC stuff. You pick this up being just a systems admin and systems engineer and that kind of stuff. And then I get into like the nuts and bolts of how HPC works, what the compute nodes are, what the cluster management systems are, how they work, what the schedulers are, what the shared storage is, how the networking works, and then what types of HPC tooling you're going to see out there. And that's kind of my overview of this talk, right? I might not go in as much depth on this one. Just depends how much time I got. Again, I don't know exactly where the wife is, but she should be back in a little bit here. So we'll run through stuff. I try to do, when I stream, I try to do at least an hour, so try to get some stuff in there. All right, so what's HPC? High performance compute. That's a term that's out there, but that kind of is like the cloud. Like, what is the cloud? The cloud's a lot of things, right? Well, the NIST has very well defined what the cloud is, but HPC, in my mind, and kind of what I've seen over the years, is it's a lot of different things to a lot of different people. You're going to get a lot of different answers. So for me, it's something that exceeds the computational needs of one system. That's a very generic idea, but it will help you to kind of spackle on everything else that's going on. Yeah, Fisherman, I think you can definitely set up a 2 VM test HPC cluster. Yeah. In fact, the one that I'm going to put in the lab looks kind of like this. You know, it's funny. I don't have anything up. Let's pull up Excalidraw, and then let's back out a little. I'm going to be putting one in the home lab, and we'll have a login node with a Slurm scheduler. Then we'll have some compute cluster of some type, and then we'll have a management node over there that we can do like XCAP management of the systems from. So I do have a plan to set that up in the home lab. Well, a plan in that I made a drawing of it. Maybe it's not a full-on plan yet. And then however, if you hear in this next few parts when I start talking about like the system skills you need, and you're like, hey, I have those gaps and I know I need to get into there, then you can talk about start thinking about how to close those gaps and learn that stuff, and then you'd be pretty ready in that space. So okay, what isn't it for the purpose of this talk? These things are HPC adjacent. I think my doctor told me to get an HPC shot one. Yeah, HPC adjacent technologies are like big data processing. So Hadoop, MapReduce, Elastic MapReduce, things like that are not directly part of HPC for the purposes of this talk. Do we work a lot of the same workloads between them? Sure, But in strictly what I've seen as HPC, high performance compute type space, that's considered something else. Just so you know, those type of workloads get run and managed and processed slightly differently. So then data lakes, data warehouses, and lake houses. There's a lot of terminology for this. All companies out there need big data. All companies out there need to store their data in a manageable, structured way so that they can query it and check it. That's what data lakes and data warehouses and lake houses are and all those things. That is not specifically what HPC is for the purpose of this talk. Do we have huge amounts of storage, like in my case, like petabytes and exabytes tied into our HPC systems? Absolutely. But they're not doing this type of structured data that you're trying to get out of this. That's not the purpose of it. They're more like genome sequences and large data sets of weather and things that themselves, once they're processed, you don't always necessarily need the raw data in the same way you might need some of this stuff. So I just need to make sure it's a little bit different. Cubicle Jeffrey Dahmer over here. That's funny. I heard Jeffrey Dahmer reference like 2 hours ago with RoboDom and Salty, which was kind of funny. All right, so what isn't it for that? Let's put that as those are adjacent technologies for this. They're not needed for this. What type of SAN storage is currently used in HPC objects? No, actually, surprisingly, Fisherman, the two main ones that I'm going to talk about, Lustre and GPFS, are file system storage. They are file system. The way the client connects is novel and faster. It's novel and much faster than a normal system. But yeah, Fisherman, it's they're going to be file level, like the same as a file share type connection. So I'll show you that here in a little bit. How's HPC used, right? Government, military. I know that sounds redundant, but when I say government here, I mean more the different government entities, and then military, I mean specifically for military applications, which are different to me, having worked with both of them. Academic, I'm heavily in the academic space. I'm currently working in an HPC environment that is all that space. Red Sly Fox 8, we have a bunch of people that are, one of our guys just was working on his CYSA. That's CompTIA, right? One of our guys was working on that as well. Yeah, big government definitely has big compute, that's for sure. And then private research sectors all find applications. I've never worked in the private research sector. Well, actually, no, I take that back. I have. I've worked in all of these now that I think about it. Caris Life Sciences was private research. We were the biggest cancer research back in like 2015. We were the biggest cancer research repository in the world. And we almost got bought by Google like twice while I worked there. It was kind of wild. Never saw any aliens, no. But medical industry, like, protein sequencing, protein folding, those kind of applications, genomic applications, so looking at the human genome, seeing how things work, illness, virus tracking through populations. This is big data type stuff. This is HPC type stuff. Some of this, by the way, this is also big data type stuff. So this can be map reduced and other stuff like that, but that's a little bit different. Hey, Twisted Seed, how's it going? We're talking through some HPC talks that I did. I was setting this up all week, and I gave this talk to my Linux group down in our Discord today. But we don't have a recording of it, so I'm just kind of going through it again, and then if anybody wants it, they have the recording. Satellite imagery, you might have a big, 10 mile by 10 mile, satellite image, and you need to see all the places where something changed along a road or something like that for military applications and that kind of stuff. That satellite imagery, you would need to process that very quickly, and you would need to do that and turn that and get that turned around very quickly. So high performance compute is a big part of that kind of stuff. Also, slower versions of that, satellite imagery in the US is used. So when you have long running power lines that are running through forested areas, and you guys have probably seen how the limbs sometimes grow close, and then you can watch these online. There's actually videos of the helicopters will fly, and they'll just have these chainsaws hanging down. They're not always chainsaws, sometimes they're bladed saws, and they will just drag them along, and they'll chop all the tree limbs, right? So we'll watch this stuff happen, right? And satellite imagery is used to track that. Next time post to HPC Reddit. I feel people there were really cool and know this exists. Well, that's awesome. Yeah, Mr. Nothing. That might be. I might do that one of these days. That might be kind of good. Yeah, branches. They chop the branches off, but with the big, they have like these big hanging circular and/or chainsaws in some cases, and it's pretty interesting. But they can track that with satellite imagery, and they'll check for change detection in the imagery between every 2 days or every 2 weeks to see where the branches are growing, right? So it's kind of a cool thing, and it saves man hours having to drive those lines because it takes them hours and hours and hours to drive those lines, right? This is where I've done this. I built the newer HPC system for NOAA. I was a big part of it. I did a lot of the Ansible and the startup configuration and like the base images of it. But weather tracking, weather prediction, NOAA ingests from over 2 million sensors daily. So they have a tremendous amount of data coming in. And then, if you guys didn't know this, I have a link later in this presentation. By the way, this presentation's completely up in the Discord. So if you're like, hey, I got to miss this, you can go download this presentation from the Discord with all the links. I got all kinds of links in this thing. To take you to different places. So feel free to join the Discord. It's down in the presentations channel. All right, so weather tracking is huge. Like we got to run these weather data sets every 6 hours. Then those predictions go out. There's free and paid for versions of NOAA weather predictions and other things. They go out to all the different rural stations so that we can get better weather prediction. But if you've never thought of this, and by the way, we send that to NOAA does worldwide weather, and the reason is because weather's tremendously important to military operations and logistics. I imagine it is important for countries as well to know, but yeah, other countries actually pay us for our NOAA weather. Like I know a lot of European countries, they get news feeds basically from our NOAA to predict what's happening with their weather. It's very important for your fishing. Yes, absolutely. But yeah, if you're ingesting from all this stuff and you have like 6 hour windows that you've got to present and create this data, you need a lot of parallel processing, a lot of data. A lot of that data also gets touched by this NOAA stuff. There's research scientists all over it running in the other cluster, so you always got a cluster up and then you got a backup cluster, and they're running against that. So we want to try to keep like an 80%. I don't know the exact numbers, and even if I did, I wouldn't tell you the exact ones, but let's say like 80%. You want to keep utilization across those clusters. You don't want them to just be sitting there, and you want to be keeping them utilized, practicing and training new models and testing and doing all this kind of stuff like that. The only one music is kind of noisy and difficult to hear. I can turn the music down. I didn't hear anybody say anything about it, but can you guys hear better there? Is that better? Turn the music down. All right. Yeah, I didn't even realize it was loud. Nobody had said anything. All right. Election tracking, people tracking, all kinds of things, right? And then, so this is how high performance compute's used. Is it all of it? Oh gosh, not even close. I mean, I've only touched the things I've touched, right? Like, and this is stuff that I've worked in heavily, but there's all kinds of other things. All kinds of stuff with HPC. So I'm going to show you guys the basic things that I can show you about how to get into this space, right? So we're going to start with system skills. These are Linux and system type knowledge that'll help you break into HPC work. So if you are already in Linux, or you're a hobbyist, and people come in all the time and they're like, oh, I know Arch Linux. And I'm like, excellent. Do you know how to do this, and this? Those are the things that are important as a systems admin. Well, a systems admin, a systems engineer will benefit greatly trying to get into HPC if they know these kind of things, right? And here's what I think your need to know skills are. So here's your need to know skills. Linux process evaluation. Do you know, right? So if you're on a system, what kind of Linux process evaluation can you do? Do you know how to do, like, let's say you do a ps-ef grep for SSH. Is SSHD running on this box? Yes, SSHD is running on this box. And we have a whole bunch of ciphers that are or aren't allowed. So maybe that's probably a custom way that somebody chose to run this. But can I tell when this was started? Do I know what the implication is that the parent ID of this is 1 and not something else? There's a certain thing that means in a system, right? If it's a 1 here, then it was started by the system, the kernel, when the kernel came up, right? This isn't something that was started later. These other things were started later, but they were related to SSHD, right? And then maybe some other things like, and when we get later on, whether or not it's running system D, yeah. So later on, we're going to look at like some schedulers and some other things, and it'll help in troubleshooting if you understand what should be on in your system. Your system has a bunch of different things that should or shouldn't be on, typically like slurm D or mbatch D, depending on the system that you're trying to use for your scheduler, and all of the subordinate or worker nodes, some people call them slave nodes still, depending on which types of nodes you're working on, they need to have those daemons running so that they're listening to the master or the main or the primary, or some people call them, there's all kinds of names for these nodes depending on which different system you're also. Hold on. Okay, so then there's the disk and mount points, right? So you need to know like df-h, what's that showing me? That's showing me how my system is carved up. This is important because if you're, and one of the things I'm talking about here with kickstart files, building RPMs, building software, kickstart files and how we carve up a disk is tremendously important for what we, when we build out a new box and we have a stateful or a stateless image, we're going to talk about those later, I expect them to be carved a certain way. I expect this disk to be maybe partitioned a certain way. This disk here has been partitioned a bunch, and this looks like, to me, that it's been partitioned according to like a CIS benchmark. So for a security reason, this has been carved up. But in HPC world, that's not always true, right? So our disk and mount points, it's kind of important that we understand what we're doing here and what we're looking at. I might want to know like so I know this logical volume management. How do I know that? Because I'm using volume groups here. I can do PVS, VGS, LVS, and I can see that I've got my physical volume is just this one disk. I've got a pretty small volume group on that disk. I've got a pretty significant amount of that disk still free, so I could extend some of these if I needed to within my volume group because I've got a lot of the volume group free, right? These are the kind of things that are kind of important to understand on the Linux side of things when we're getting ready to work in HPC world, right? Network and networking tools, right? So, I could do IP adder, and I can see that in this interface, in this system I have an ENO0, I've got an ENO2, ENO1, what am I thinking? ENO1, ENO2, and IB0. I've also got a loopback, but loopback is always there in any of your IPv4 type environments, and it's always got a 127.0.0.1 home address, right? But then I can look at this and I can say, well, I'm having a hard time getting out to the internet. I can't ping www.google.com. Can I? I cannot, right? Oh, I can, right? Took a while. But then I might look at this and go, okay, well, I need to figure out where my system's trying to send traffic. So I do an IP route. And then IP route shows me that if my system doesn't know where to send something here, it defaults to this address here off of ENO2. ENO2 is this address here. And I think about it and I go, So what I thought about earlier when we were talking about this was that this was my primary interface. This is not my primary interface. This is my primary interface because that's my default that the system sends traffic out if it doesn't know what to do with something. If it's going out ENO1, it's going to this address range. This is a tiny little /24 of only 254 usable addresses, right? My InfiniBand network is only 254 usable addresses as well, as is whatever this ENO1, maybe other address that's off of my ENO1 as well, right? So my point is I can start to figure out what's going on here. And if I'm a systems engineer or systems admin in a high-performance compute environment, I might need to be able to troubleshoot these tools. Let's say my InfiniBand isn't working right. I may need to do IB stat and see, what type of card do I have? Do I see that I have an active state with the link up? Maybe if I do IB status, I think IB status shows me the speed. Yeah, so I see that I got 100 gigabit per second 4x EDR type device. Maybe I didn't know that, right? And now I know that. And maybe I want to check that against all my devices to see what my device's speeds are. So what I could do real quick, and I'm going to show these. Actually, I'll show it now a little bit, but XDSH to my compute nodes, and then I can do over on all my compute nodes IB status, and then I can do a grep for rate, and let's go ahead and throw this in a quote so it's all in there and it's not coming back after. And I can just run this real quick on all my systems, and I see that all my systems look like that. But I can also, and I'm going to show this a little bit later, I can do an XDSH back -C, and I can simply look for systems that are outliers, systems that don't have this 4x EDR, and maybe I need to be on EDR, not HDR or FDR. I don't expect anybody to understand all that now if you don't work in that space, but know that those are technologies and speeds that are kind of out there. Okay. Okay. So, yeah, this is a way that we use XDish. By the way, XDish is a set of commands that's specific to XCAT, and we're going to look at XCAT here in a minute. But we're back over here on Linux administration. People that got here a little late, let's just talk real quick. I'll pop this up. This is our stream goals right here. Learn about HPC and how to get skills in that engineering area. This is also in our Discord. So EDR, I think, stands for Enhanced Data Rate, if I believe. I'm not 100% sure, though. But that's funny. We need to know file system permissions, right? Like, obviously, most of us doing Linux in some way could tell you something like ls-ld on root. We could look at this and go, okay, well, that's against the root home. That's the root's home directory. And over here, I can see that it's a directory. I mean, sometimes you've got the colors to help you. Oh, we're on an ad break, so I'll hang out here for a second. We'll check on Ranger Dog during the ad break. How's that? There's Ranger. Hang out with Ranger for a little bit on ad break. Ad break, Ranger check. There we go. I think the ads are running. It says the ads are running. Give a minute. I'll check my phone for a second, see if the wife's coming home soon. We'll pull this all out in post-production. I'm just kidding. I don't do any of that. I don't really do any of that post-production stuff. That's why you get what you get here. All right. Give it a second, and we'll get back to it. It's 30 seconds more, in fact. Yeah, Inspector, I get all mine off of Amazon for the most part. All right, am I back? Am I back from the ad break? We were just checking on Ranger during that. Okay, file system permissions. You need to know them. You need to have a general idea that, you know, this D right here says that I'm looking at a directory, even if the color doesn't help me out. By the way, not all operating systems give color like that, and your shell doesn't always have it anyway. So you can remove that from your shell with aliases, right? You should know that this is owned by root as the owner, the user owner. It's owned by the group owner of root, so the group owner is here. Read, write, execute. You only have read and execute as the root owner, and read and execute is all you have as the group owner of this root directory. Everybody else gets nothing for permissions, right? That seems really simple, but then you might say, well, do I have any FAC, let's see, get FACL. Do I have any extended file system permissions on that? Whoops, root. And, well, are we using extended file systems? So mount grep. Root's not going to be on its own, but let's just do a mount and see in this system when we find the... we could look for it through... we can actually do it through... Yeah, EXATTR. Right? Grep. We could see if anything in here is using the extended attributes, right? And I think there's another one too. I always forget what it is. But the point is, you might want to know, you might want to need to know these things, right? And also one that I've seen turned off everywhere I've ever been, but some people swear by it. You just need to know your SE Linux stuff as a general rule. You know, you do an ls dash capital L, capital Z on root, and you'll see if there's any permissions set and what we call labeling. It's additional labeling for access control. However, if we do SE status, we see that SE Linux is turned off, and we can do a more on SE Linux config, right, and see that it's also turned off. And then you can, if you needed to, you could redo labels and stuff like that. I showed that a little bit earlier. This isn't really the point of this, but you need to kind of understand these things. System building and boot process. Because the fact that a high-performance compute system is almost always air-gapped, we need to understand how to build our own RPMs. Sometimes we got to download software and build an RPM, and that package will then go to all of our different compute nodes. So sometimes we have to build our own RPMs. That's a skill you need to kind of learn and work with. We need to be able to build software from source. So if you've never done a configure, a make install, make and a make install and get everything working, and maybe go through, dependency nightmare and have to go download new versions of libraries and stuff. That's a thing you still have to do in the high performance compute space. Everything is not in yum or apt-get, and even if they were, they would be air gapped, so you wouldn't be able to get to them anyway. So Linux administration, those are things that are kind of important. Automation is using tools to extend your capabilities to multiple systems, right? So I wouldn't say that you need that in I wouldn't say you need Docker much in HPC. I've only seen Docker like about this much in HPC, and it was with Cray's Shasta system, and then Cray's Shasta system's pretty much gone. Red Sly Fox, are you asking me about the RHEL cert? Or are you asking somebody else? All right. You need to understand how to loop and do system scripting tools. So, you should be able to loop over a set of systems and be able to, so if I do node ls compute, right, and I get this list of systems, I should be able to do something like this, for server in, I'll do it the more modern way, this way, right, something like this, for server in compute, oh, that's kind of low for you guys, hold on, for server in $ node ls compute, do echo, I like do it like this, checking $, so node compute, whoops, and then something like SSH compute, server rather, oh man, what am I thinking, server, and then SSH $ server, something like this, and then I'll say like host name or something, I don't know, done, right? And then this will go and check all the nodes and see if it can get in them. But what server are you working to? Red Sly Fox, just because you ask, certs. There's my certs if anybody cares about that stuff. But no, Red Sly Fox, none of this stuff is certs based. I'm showing you high performance compute stuff. So this isn't necessarily, I don't even know if anybody's got a cert for high performance compute. Yeah, those are all in the last 2 years, by the way. Well, except for the CISSP, I got that. Yeah, I'm kind of like a cert junkie, more for fun than anything. But those are my current certs right now, and then a list of the old ones down there. Okay, so yeah, and also, I mean, if anybody cares, I've been teaching this stuff for 15 years too. So at the college level, so so I'm trying to get through this, but this is a way to loop. The problem is, and they still haven't shown, no, I haven't seen any cool aliens yet. The problem with this, though, is there's not a lot of control along this loop that I'm using right here. It's just linear, it's just going to loop. It's not going to have, there's no error checking. There's not things that we get with other tools, but Perl and Python and Ansible. Ansible is one of my favorites for doing this stuff. Do I have Ansible on here? I don't have Ansible on here. If I had Ansible on this box, I could show you some Ansible commands. But the point is I can hit all those nodes and extend my workout so that I can hit a bunch of systems instead of just typing and fixing things on one system one time. So looping and scripting tools are like key to this. They're very powerful at getting you to not just have to be one person sitting at the keyboard. You can, you can extend yourself to not have to be working all the time. You can just push stuff out, stage it, run it on different nodes. And then one of the things, I'm going to press up a few times because I'm lazy. Right here with XDSH compute, I can hit all of these nodes and just get, this is where I was saying here, you need to know your XDSH and XDSH back commands. That's only if you're using an XCAT system. And this is what it might look like. All your nodes would respond, except for one that's down, or IB status isn't even on that. So that box, so I could look at this real quick, and I would know, for some reason, HCC 17 is down. I don't even know what, yeah, I use Terraform, Mr. Nothing, yeah. Yep. I got Terraform up there, and I used to do a lot of Terraform on stream where I would like deploy a bunch of stuff up to the cloud, pull information out of Vault and send it up there. I haven't done that on stream in a while. Terraform doesn't have a lot of place inside of HPC right now that I know of. Not a lot of people are using it in the HPC space because the tooling that's there is pretty good. So, all right, so check this out. So what I would know immediately is this node's down. I got to go figure out why that node's down. This node is there, but IB status is not there. IB status not being there tells me that there's probably a package missing on this box. So I can figure things out very quickly. Hey, Sending Ground, hopefully you guys made it home safe after your long drive. I'm just kind of talking through what I had done earlier as the presentation of like high performance compute and all that kind of stuff. So yeah, and then what other things do we need to know, right? So we need to know how to do our looping and our scripting. Whatever tool you're going to use, you just have to be powerful and good with it. The other thing, real quick, if I wanted to take this and do that XDSH back -C command, this is just going to aggregate everything for me. And this one, yeah, the one system had the command not found. All of these systems came up like this. This is a really super useful command because at the end of like maintenance, and you know, with any type of maintenance, we do the best planning we can, and then we go hit our 1,000 nodes, let's say, and we're like, okay, our 1,000 nodes have all been patched and they're back up. But there's this rule in engineering and in life called the Pareto rule, or the 80-20 rule. And what the 80-20 rule says that 80% of your problems will come from 20% of your inputs. Roughly stated in systems world, you know, 20% of your systems are going to give you more problems than all the rest put together. That's kind of what it roughly translates to. But out of 1,000 systems, you're probably going to for sure have at least 20 that are down. Well, this is a real good way to see, like commands like this, across all of my compute nodes. All of these guys, basically, if you want to think of it as like towing the line, these ones are all towing the line. I can see them, they're up, they're showing me good values. This one over here, what the hell's he doing? This one over here, what the hell's he doing? It's the same reason in the military they make you stand in formation. It's real easy to see who's 8 up and doesn't have their shirt blouse buttoned the right way and doesn't have their hat on the right way when you look down a line and see a bunch of people that aren't standing right. It's super easy. Well, it's the same way with this. Super easy for me to see everything. Nodes in a cluster, I've worked with, when I worked with NOAA Weather, we had about 2,600 in each cluster. I'm up, he sees me, I'm down, yeah. That's a little military one too. Yeah, but 2,600 in the, out in Virginia and 2,600 out here in Phoenix are some of the bigger ones. You can have smaller, my cluster at Northwestern's smaller than that, but it's still, we tend to think about the compute of a cluster in the overall number of cores we have. So in this cluster here, I was showing this earlier, I might say, looking at this, I might do something like nproc, right? And the xdish commands, again, are just specific to, they are a command to go hit a bunch of your nodes with a shell, but it's specific to XCAT, so you got to be using an XCAT system. But look at this, it's That's a little over 100. That's another 100. That's another 100. So over 300 cores in just this little test cluster that I have. Tomo's here. Everybody's here. Guys, I got two of my four brothers in this chat right now. Baraga and Tomo. They're my actual literal brothers. Anyway, so we're going over this stuff. Ansible. Ansible's a great way to personalize over the top of systems once you've built them, right? So anyway, so real quick, we started off here, HPC System Engineering Topics. We talked about my overview. We went through what HPC is and isn't for the purpose of this discussion. Then we talked about how HPC systems are used, government, military, academic, private research. Then we got into system skills, things that you need to bring to the table to be ready for this, right? Actually, both of these brothers work in tech as well. One is a, he'd be like an OpenShift lead for the company, and then the other one is a data analytics guy. So they do all that stuff. So there's automation. Next thing I really think that you need to bring from being a Linux engineer is benchmarking. You need to understand the system and applying ceteris paribus. Ceteris paribus tends to mean it's a economics term, and it means all other things held equal. Like, we know that there's thousands of variables to economics, and we know that there's thousands of variables within a system. But if we hold all the other ones the same for now, and we change this one, we tweak this one knob, and it gets better, can we say it's probably from tweaking that one knob? Now, you have to understand assumptions here, and I'm not trying to get into economic theory. That's a whole different concept that I'm also pretty good at. I do have a couple of master's degrees in that kind of stuff. But ceteris paribus is the idea that you can hold everything else the same for the purposes of a discussion, and everybody can understand that. And then in this case, figuring out system speed, applying a change, and then checking it again for the delta. The delta, that triangle, means change. So if you're ever, in an engineering sense, and you're working on something and somebody shows a delta, or they say the term delta, they mean the change in rate, or the change in speed, or the change in whatever, right? So, LinPack, that's a tool for benchmarking HPC systems. It's standard for the top 500. If you want to be one of the top 500, over at top500.org, that's where everybody goes and tests to see where they are in the world. All the fastest in the world are there. We're going to be looking at those here in a little bit, but LinPack is one of them, right? I'm a big fan. I touch individual systems often, so one of my favorite is just the simple Linux DD command. With the DD command, you can test write and read speeds into a system very efficiently. You can test how fast you read data out. You can test how fast you write data in to a shared storage by any one individual client. You can do it by multiple clients at a time to verify that you're getting the aggregate throughput that you expect to. And then one that I also like to use, this is I called this Slurm testing, but you could also call this like day in the life testing. You have a known job. Maybe you know this job takes five days to complete, and you know that job uses 40 cores or 40 nodes or whatever you know, and you know that there's, again, you're keeping everything else the same. So across the course of a week, Monday through Friday, you run this job. And you know that you're going to experience some slowdowns because other people are running jobs in the cluster. That's all for the cluster management software and the scheduler to handle. But then we make a change. We add more disks. We add we go from an FDR to an EDR disk disks. We go to faster disks, and then we go to faster network backplane. And we expect it to be faster, but how much faster? Well, we run that Slurm test again, and instead of taking the regular 5 days, it takes 3 days. Well, that's pretty good. We got a speed increase, and we can test it a few more times to make sure. But again, somebody else might say, well, the teams that are always running stuff from the business college, they weren't here this week, so it's obviously going to be faster. And you're like, yeah, hold on. We're assuming everything else is the same for the purposes of this. So Slurm testing, also known as I can't hear Slurm without thinking Slurm McKenzie from Futurama, right? The party worm, Slurm the party worm. All right, so that's benchmarking. Now, even though I've alluded to and touched some HPC, by the way, this is my HPC cluster that I use at work for testing and training. I train people on this stuff. I build training for different companies through my company, and this is my test cluster for that. Let's talk about some HPC concepts and technologies, right? Everything else I did was just alluding to, we talked about HPC. Now we're going to talk about the actual concepts and technologies that I think you need to know. Again, this whole talk, the whole reason I'm giving this is to say, if you're already a Linux, admin or engineer, and maybe you're a hobbyist, but you want to bridge that gap and get some of the skills and talk about some of the technologies to go apply for HPC stuff, that's what this whole talk's about. By the way, we talked about this already. Here's the actual stream goal right there, boom. And then this whole presentation with all the links I have in it is up in our Discord. So you can hop in Discord if you want any of that stuff. Discord's real easy to find. Just do ! Discord. All right. So the first part, this is like the first component that's pretty useful, I think, to understand is your compute nodes. Your compute nodes are the fundamental component of HPC, right? They're the things doing the work. Compute nodes bring to the table CPU, GPU, memory. They very rarely bring disk. Their disk is typically either a single disk or maybe a RAID 1 mirror so that we can get them back up and running quickly. But as you see with like this concept of stateful and stateless, we almost don't give a crap about what's going on disk-wise on those. This varies greatly from big data type systems where, like with Hadoop, everything brings its own disk and it becomes part of the HDFS cluster. We do not do that in high performance compute from a, let's say from like a general standpoint. Are there places that are doing it? Absolutely. Is there anything wrong with it? No. It's just we are going to have a super high speed network and a super high speed file system. That's what we're going to connect to and treat as our shared storage. We're not going to do us dicking around with slow ass disks on a backplane, slowing down the compute nodes from doing their compute stuff. That's not something we do in high performance compute space. So take that how you will. Hadoop runs for HDFS. It runs on every node. On all the controllers, I think it runs 2 Java processes, and then on all the nodes, I think it runs 3 Java processes. So there's a lot of stuff. Data and compute. Yeah. I'm just telling you that's kind of the way it's done in the HPC world. So we don't do it that way. Yeah, King Buns, this is really the stuff that, let's say, starts to be like, I guess, the interesting stuff. I've got a lot of links coming up of things to go spin off and study more, especially for you guys that do programming. This stuff may get really interesting for you. Hey, thanks for the follow, Cafe, yeah, whatever. All right, so we put these compute nodes in. Schedulers can add compute nodes to different work queues, and then we can prioritize certain jobs and tasks, right? Sounds like safe haven for curmudgeons who don't like the new fan. Yeah, it's actually true, and I'm going to talk about that here in a little bit when I get to like the Shasta system and why we were just like, I don't like Shasta because I'm an old Unix engineer. I watched it happen, but it's true. It really did. So let's talk about stateful or stateless images and stateful and stateless nodes and how it works. Stateful gets installed to that local disk I talked about. Now, when the system boots up, it will boot off of HD 0 or whatever your disk 0 is or whatever you want. You can point to a different disk, of course, with your grub, which is also, by the way, again, back to that old skills you need. How do I boot and that kind of stuff? Very important. But a stateful system will persist data in it through boot. So if you boot it off and bring it back up and you've updated GPFS in it, you will still have the new GPFS installed to that disk. A stateless image is not ever installed to that hard disk on the box. That hard disk on the server, not really used in a stateless image. Stateless images are built from a RAM disk or a net boot that is pulled on every single boot. So I got to explain something here because you've got your stateful fat system and then you've got your stateless, which is sitting here like this. I got to explain something. There's another term that we talk about a lot, especially in Kubernetes, that's called a immutable node, right? Or an immutable pod. Immutable pods can't be changed because they're read-only. This stateless node is not immutable. What do I mean by that? This stateless node, if it goes down and comes back up, is the original node, yes. But if I have a stateless node up and I go put a web server on it and I run a web server on it for 3 months, That's cool, man. We got a web server. We got some Grafana on it, and that box turns off one night and comes back up. Everything's gone. So it's not immutable, because immutable means unchanging. It's like I'm trying to hammer on it with like a pen, but it's a piece of granite, and I'm like, I can't etch into this because I'm using a pen, right? It doesn't work. That's how an immutable pod works. And we use immutable stuff for security. We use it for speed, all kinds of other things inside of the Kubernetes world. Anyway, so where I'm going with that is stateless images are not immutable. Don't think they are. But when they go off and come back up, they've forgotten everything. I read a joke long ago. I need to go find it, but it's this meme, and it's like, it was joking about the difference between how guys and girls shower. You know what? If I got to explain it, it's not that funny. But anyways, I'm not going to tell it. I'll go look it up and drop it in our Discord later because it'll be funny. The crux of it was guys use their towel after they shower to dry everything off, and then they hang it up, and the girl's like, well, what about, you just touched everything? He's like, the towel forgets everything by morning. That's how random disk. All right. Anyways, okay, I'm having too much fun here. They're controlled by a scheduler, typically Slurm or Platform LSF, and they're controlled by a daemon that's running on them. The towel always remembers. Slurm is running Slurm-D everywhere, and Platform LSF is running Batch-D. Batch-D is the name of the process, right? And we're going to look at them. I'm going to show you guys some pictures of their architecture and send you over. When you're done, if you look at this actual PowerPoint that I've got here up in Discord, you've got enough power. If you got enough links to go read for like days, I think, if you really wanted to. But this controls authentication is provided by the Munge-D daemon. So now Munge, I think I might need an E on that. But the Munge daemon has to be running for Slurm to be able to send links. Platform LSF uses a different one. We'll try to find it. I'm not really too worried about how authentication occurs in that space. But just know that a scheduler has that. Why you want to know that when you're actually in charge of a cluster is because, back to that, all those compute nodes we were looking at here, I need to be able to hit all those nodes and verify that Munge-D and Slurm are running. So those are checks that I might do, right? Then the compute nodes are going to be connected to a shared storage space by a high-speed network. That's always true. That high-speed network should only be passing storage traffic. And when we have a separate network for only high-speed storage traffic, we call that a storage area network. As differentiated from a network-attached storage is something sitting out there sharing network bandwidth with all the rest of the management traffic. That is completely a different concept than a storage area network, which is our own links separate. And that looks like this. So our management nodes, they're over Ethernet here on the white, and then we've got InfiniBand network, which is our high-speed network on the back end, connecting all these devices so that they can do just storage data. There's no management traffic over this blue network. All right, we'll get to that in a little bit. Compute nodes, we have to have in-sync versions of codes and libraries for execution of jobs. Slurm doesn't care what it sends out to these different nodes. There is an assumption within a job pool that everything's the same. So this is one of the reasons we build things like this, stateful and stateless, everything coming from our XCAT node, because then all of our packages, everything is set the same way. So all of these nodes basically could be clones of each other. All right. In the really big HPC compute clusters that I've worked in, we try to have the same size and ratio of CPU to memory. So if we're running, let's just say, for example, the most recent big cluster I worked in before I came to work at my current college for research was 256. We had, wait, no, let me take that back. Sorry, take that back. We had 512 cores per node. There were 512 cores per node. They were all liquid cooled. And we had 2 terabytes of RAM per node. So these nodes were there were 512 cores and 2 terabytes of RAM per. And I think that when you break that down, it's some amount of gigs. I want to say it's 4 gigs per core. And that was a standard ratio across all of the nodes in the cluster. Must be off, but this was interesting. Oh, yeah. Yeah, thanks for coming by. Hopefully, if you want more persistence of what we talk about, jump down in the Discord and all that good stuff. Okay. So, tend to be the same side. Standardization makes job execution and scheduling more functional and easy to work with and troubleshoot. Those are big things. Typically, we'll call them compute nodes. Those are just regular nodes of whatever size we have. High memory nodes will be nodes that have a higher memory to CPU ratio. And sometimes those are needed, like when I was talking about the satellite imagery earlier and you were holding 10 square miles of a high resolution image, and then you had 6 hours later another 10 mile square high resolution image, and you were tracking up and down all of the roads and stuff and looking for shadows and change detections and disturbed earth and all of those things, you needed extremely high memory to hold all that, right? That kind of stuff is high memory. And then GPU is like when you need to do GPU type processing, and a lot of people have moved over because GPU can be much more dense than CPU for the same amount of cooling in some cases. So GPU nodes will be there. And typically compute will be, your base set of nodes, and then maybe you'll have some set of these and some set of these for specialized work. Not all clusters have all of these. All clusters have base compute nodes of some type, whatever that is for them. And then these would be, a change from this, some kind of delta off of whatever you call your base compute node. If your base compute node just has a tremendous amount of memory and GPUs in it, that's your base compute node. I mean, that is what it is. But these are typically based on, this would be your compute node, and then if you have other nodes that come in, and then your scheduler can control them based on pools that you assign, right? All right. For people that got here late, one more time real quick, I'll just talk about, this was our stream goals, right? Learn about HPC, how to get job skills in that area of engineering. Most people that have hung around or listened to me have some skills in the Linux space. Our goal as the Professional Linux Users Group is to take your skills as whatever hobbyist you are as a Linux engineer, or whatever types of things you like to play with, and make that into, give you the skills to be a professional. That's our goal in this space, right? So vendors do sell completely put together. Oh, looks like we're on an ad break. Well, if we're on an ad break, we'll do a ranger check. It says we're on ad break, so we'll go do a ranger check. Ranger has not moved much. He's been kind of yelping the last couple weeks. I told you guys about that. We got him on all kinds of painkillers and steroids now, and they're going to check on him in a week again and see if he's gotten better. I think he's been getting better, but maybe I'm just optimistic a little bit. But yeah. And then I don't know if my brothers are still around, but we were talking about if any of you guys ever saw the Rick and Morty episode with there's a Rick and Morty episode with the dogs and the dogs take over. I think it's like the second or third, maybe even the fourth episode of Rick and Morty ever. It's very early on. Same first one with Scary Terry in it, and they're going into the dreams and stuff. And there's a scene where Grandpa Rick makes Morty's kidneys fail, so that, and he's like, "You're making my kidneys fail in the dream, right?" And he's like, "Yeah," but he actually makes them fail. Well, anyways, in the dream, the dog is like, "We are not them. I will spend up to half my kingdom to keep them alive." And he's like, "Would they do it for us?" And he's like, "We are not them." Well, anyways, that's how I feel about Ranger. Like, I told the wife, I was like, anything we need up to half my kingdom, we'll save Ranger. So that's an old expression if you guys have never heard it. All right. So Ranger's good. He's resting comfortably. So some of you guys should be back from your ad break. We were just watching Ranger during the ad break. So what we got to was, cluster management systems are for people that want to build their own solution. There's open source ones. You can have vendors put these together for you. Cluster management needs to have an inventory or a database of some type. It needs to be able to control those systems, typically at the BMC or IPMI level. We need to be able to build, remove systems from the HPC cluster. And they need to have, well, they don't all need to have it, but stateful and stateless node builds are included in all of these ones down here. So XCAT 2 is the first one I have linked here, and it's going to pop up. And XCAT has an architecture that kind of looks like this. Some of the things about XCAT that really set it apart and make it useful: it is open source, it is controlled by IBM, But on your management node, you run xcat-d as a daemon, right? xcat-d running in an environment and with its little database of all objects. Everything's an object. Everything can be dumped out to a CSV value. So you can have a comma-separated value of everything that's out there. You can then define DHCP in your environment, so you can assign how addresses are how systems come up. TFTPD, so that you can move files to your systems. DNS, NTPD, syslogd if you want to syslog all your messages back. But then what you define at this database level is you define operating systems and postscripts that are going to run on boxes when they come up. You can have different service nodes over here that maybe connect to other compute nodes and help build them out. And it allows you to have like the centralized place where everything's controlled with XCAT. So in my environment here, this is an XCAT environment that I have stood up here. I can do stuff like node ls for compute, right? And I can see all my compute nodes right there. Again, I think I was telling the guys earlier, my boss has changed this all up, this environment I'm in. So I have a lot of stuff that I don't necessarily know what's going on. But I can do tab dump for OS image. So these are OS images that I created in this cluster. And here they are. Remember, I said I can tab dump everything into or I can pull everything out as a comma separated value. Here's a comma separated value. I've got this CentOS 8 install compute. I've got this CentOS 8 stateful management node. I've got a CentOS 8 net boot compute. So now you might say, what's the difference between an install and a net boot? The main difference between an install and a net boot is that right over here, when we call something install, well, when we call it install over here, it's an arbitrary name, it doesn't matter. But when it's an install over here, that means it's a stateful node. When it's a net boot, it will always go and pull images every time. So let's go xdish these nodes real quick, and I'll show you how I find, because again, I had like completely different named nodes in here like 2 days ago. My boss changed all this around. I'm going to go to each of these nodes and run proc cmd line. Proc command line shows you how a system booted to its kernel. Tremendously useful. But here's my HCC01 node, and I see that the boot image for this comes from HD0. That means when it's HD0, that means it was installed to this system, and this is a stateful image right here. It's a stateful image. HCC02, same thing. HD0 is where it found the Linux kernel. That's where it found on a boot sector, the Linux kernel. These two, the HC01 and HC02, are for sure stateful, fat, if you want to think of them, stateful images. However, HCC03, that's a net boot. Look at that. That pulls its image URL is pulled every time this system turns on. It goes and it pulls this image that I packaged up on this box and pushed out there. So that does it every time, HCC03. HCC04 does that same thing. HCC13 does that. HCC16 does that. HCC14 and 15, 14 is fat again. It's a stateful node, and then this is a net boot. So anyway, so you can find that real quickly, and I might be able to, if I needed to, I probably could just do. I could probably just sort this down pretty quickly and do something. Maybe I could do something like this and just say awk print $1, oops, $3, and then see if that comes out. Oops, yeah, hold on. Let me double quote this. Yeah, so wait, nope, that doesn't give me. Oh, because that's awk print. Oh, that showed less. Hold on. 1, 2. No, it didn't. Okay. Well, I guess I could do it this way too. I'll show you guys this way. I would do it this way, I guess. I could say grep boot and then just do my xdish xdsh back-c, and this would show me real quickly. That wasn't so useful. But I would see that 2 nodes were at least on this, and then all my other nodes were on some other thing, because they're not unique. Well, there's probably better ways to get around doing that. Yeah, because the node name is different. That's what the problem is. Okay. Anyways, doesn't matter. I just was showing you guys some things that you could do. But XCAT does all of that. Shasta was something that we were originally using Cray when I first got on the NOAA project. Cray is now owned by HPE, and Shasta here, while it was wonderful, the reason I mentioned it, even though it's not big, is this. It's really just now regaled down to one specific little blog post. I don't think it's really used anywhere anymore unless it was already deployed. But here's what it tried to do. It tried to implement Kubernetes, and it really had some cool stuff going on with Kafka. This is where I learned Kafka, was in here. So if you guys have seen me do Kafka projects or any of that stuff, this is where I learned it, was working with Shasta. Now, it used Kafka for reporting and logging. It used Kubernetes to kick off Ansible playbooks all over the place, and the management was really novel. However, we kind of joked around about it earlier, and I think he left. Lemnine left, I think, but it was really like a bunch of us kind of old, Linux engineers going, do we really need all that though? And Shasta was a bit over the top. But what happened with us that kind of saved us was Cray got bought by HPE, and they brought in HPCM. So HPCM is a pretty good tool. It's a functional tool. It does its management stuff fine. It also has a GUI and non-GUI support. And you might say, you know what, we're command line guys. We do Linux, we do command line all day. Yes, however, let me tell you, even across like maybe 20 engineers, I'm going to tell you, probably in the average company, over 20 engineers, most of them probably aren't command line people. So having GUI for people to get in there and do some of the work is fine in my mind, because I can still check it with the command line stuff. I'm still going to do everything I can over the command line, because that just kind of resonates with me and that kind of stuff. But let me just tell you that you're going to find that this makes other people able to get into the cluster and help with management, having some of those things. I'm not sold heavily on people using GUIs that can't understand command line, but that's for a different talk, right? That's not necessarily germane to this conversation. What I wanted to show you, though, is you can come in here, you can get all this documentation. I've got this all linked up, and it shows you a little bit about, they do stuff instead of XDish, they have PDish, and then they can PDish to a bunch of different nodes and see what kind of output you get from the different nodes. So they give us some examples of how PDish would work and that kind of stuff. And, it's just another way to do admin distribution to a bunch of different systems. They do CMU, PDish, and there's a bunch of other stuff. So feel free to look at that. This one is heavily used in high-performance compute right now, as is XCAT 2. Those are probably the main two that you would want to study. And we're going to have XCAT 2 in our lab here pretty soon for ProLug people that want to do it in our lab that we have. So, all right. Schedulers, right? Schedulers are responsible for tracking jobs. Everything that comes into the cluster, everything that runs on any of those nodes is coming in through the scheduler. So users have to get permissions to run the commands. We need the users to drop those commands off in one localized place typically. Sometimes we call those login nodes. And the reason we do that is because the rest of the cluster is air-gapped off. You're going to find out here in a second that the security in HPC systems tends to be pretty lacking. And we get away with that because we're air-gapped off away from other networks. The security person in you should probably dislike some of the ways we do stuff. Like some of the ways that like the way MungeD works, the Munge daemon, I'm not really a big fan of that from a security standpoint, but it works, right? And then anyway, so schedulers are going to allocate jobs to different nodes for execution and tracking of job completion. There's databases that can be run, and those databases can keep track of who's run what across the cluster. You can have jobs can be limited to wall or system time execution. Whenever we talk wall clock, we mean the actual wall, like the actual time of like Earth, the time that we exist in. But your system also has system execution time. So we can limit a job to a wall clock and say, hey, your job better be done in 7 days. But I saw this even recently. Somebody kicked off a job that had it 7 days, and it was down to its last 2 days. And he goes, wait, can I get some more time, because I'm not really using a lot of system time. It's actually waiting on a wget. Wget just means it's downloading something from somewhere, right? And we were like, yeah, I mean, I guess so. So we gave him like 10 more hours or whatever. So schedulers can add wall time. Typically, wall time is what we add. But you can also base it on system execution, like how much are you using and that kind of stuff. Different jobs can have priority over other jobs. By default, we can have users dropped into a lower queue. Users can't see certain nodes, all that kind of stuff. Jobs can be paused and restarted, but I have to tell you, the code being executed has to be able to handle that functionality. It has to have, maybe it has checkpoints in the code, and maybe they're writing out to their own little cache of what's been done, so that the next part that comes along and says, hey, do you have a cache, or is there some memory of what's happened? It's like, yeah, it's all here, and then it just keeps going, right? So you need to be able to do that. So let's look at Slurm real quick. Slurm, big common one. It's from SkedgeMD. It is an open source tool, and here's what the architecture looks like. You have Slurm CTLD, so Slurm control daemon, is on any of your controller nodes. You can have one controller node. You can have multiple controller nodes. Typically, we would put a secondary Slurm control daemon on a different node. And then the Slurm DB is optional, but it is recommended because it can keep track of what's going on. Can you add time to a scheduled job while it's running? Yes, absolutely. Absolutely. Yep. Yeah, every time I do a Slurm, so it's an S control command. So here's all the commands down here. They all start with S. That's one of the nice things about Slurm commands. But it's an S control command, and you just add, you say S control dash DD, the name of the, you give a job execution ID that you have that was already set up, and then you just add the time to it, and you add it in hours, so it's like 14 colon 00 colon 00 is what it looks like. But for Slurm to control these nodes, Slurm daemon, has to be running on all of them. Pretty easy, right? So the Slurm controller up here is running, and it's got all these jobs down here. Now I have Slurm set up here, provided it didn't get blown away earlier. Cat Etsy slurm.conf. And I'll show you guys here that what happens is there's a bunch of base configuration things up here. In fact, in most configuration files, when you see stuff like this just means the default has been accepted, right? You guys that have been in config files know that. These here mean, well, we might be dealing with something different, and I might have changed these. But when they're commented out like this, you're just taking whatever the default value is of the system, right? So I want to show you something here. My nodes down here that are my compute nodes for Slurm, before, again, my boss changed this all around, they're down here, and compute nodes QTCMP 01 through 04 are these nodes. That's their memory, 128 gigs of memory, and their sockets per core. They have sockets 2, and then they have their cores per socket of 16, and then threads per core is 1. Now, this is where this kind of gets interesting. My boss gave me, in these 4 nodes, when I first built these, one of them is different. One of them actually is 2 cores, 2 threads per core. And the way you check that, by the way, is you go do an nproc. Well, I got all different nodes now, so it doesn't really matter. But so you do your xdish like this, and then you would just do a cat proc CPU info. I really should just do this on one node. This is gonna like blow up my screen, but I don't care. And then what I would do is I would say here, ID siblings. I always forget where it is. Anyways, this is something you would go find. But my point is, for Slurm, they all have to be the same. Very common, simple to understand, is open source. It's found in half of the top 10. So of the top 10 on the 500 list, half of them are currently, right now, running Slurm. So if you want to go see the top 100, or top 500, you just go to top 500 supercomputers, and it's top500.org. And if you've never checked this out, this is kind of cool. I'm going to link it over to you guys. What you do is you go to the lists and you find the most recent ones, so June 23. And this is where Cray, which was bought by HPE, so see how it says HPE Cray, they have blown over the top of the former supercomputer Fukagu. And I remember when this one came out. This one came out, would have been like early 2021. Yeah, somewhere in there. This one had 7.6 million cores, so that's its cores. And it's petaflops, so that's floating operations per second. Its petaflops is 442, which is pretty big. In fact, look at how much it blew away the next one. That's an increase of nearly 50% from the last one. Do you guys see that? 309 to 442 is nearly a 50% increase. But it went from 442. This is the second fastest supercomputer in all the world. They blew over the top of that by 300%. Yeah, that's 300% more right there, almost, roughly. A little under 300. Let's say like 290% more. They blew that out of the effing water. Now, you can go back and look at all these and see, like, and they also keep track of their power. So how much power in kilowatt hours are they using? And that's, part of it because people are trying to be more green. There's another one that they're starting to track now with statistics around like how green they are as well. Like the green, which ones are the most efficient for what they're getting. And that's a slightly different energy efficiency, gigaflops over watts. I've never actually looked at this before, but I just knew that they were looking at this a different way. So here's the rank of the most efficient, but it's 255 in the top 500. So it's not one of the fastest systems, but it's the most efficient by barely any compared to this one that blows it out of the water and everything else, right? So anyway, that's a fun one to go look at if you guys want to spend some time in there. Platform LSF. It's IBM proprietary. Just ask OpenLava. It's found in many HPC government and research systems. All the commands in here start with B. So when you want to check the jobs, so when you want to schedule a job, it's like bschedule. If you want to check the jobs that are running, you do bjobs. So I always think it's funny. But Platform LSF right here, they talk about how this works. There's your cluster. Inside a cluster, you've got the daemons and processes. So on the master candidates, they're running master LLM and PIM and mbatchd, res, sbatchd, and mb scheduler. That's what's running on the main node. So if you're troubleshooting stuff, you need to be able to know that that's on the master nodes. The master candidates are waiting to become the master node. Now look, I know nowadays that this has changed terminology for a lot of companies. That probably would be main nowadays, but IBM still has it as master. Some people have changed all of those terminologies over. Your compute nodes, to be part of this cluster, have to have sbatchd, res, lim, and pim, and those jobs all need to be running. Now, what are those jobs doing? Here, it says it all right here, what they're doing, right? And you can go read about them and play with them and that kind of stuff. So I gave all that as extra stuff to read about. IBM proprietary, ask OpenLava, and I linked to some drama that happened back in like 2014. I was working with Platform LSF when this happened from IBM, and OpenLava, they did a port from, because Platform LSF used to just be LSF. It was whatever LSF stood for. Platform LSF stands for Load Sharing Facility, yeah. So it was Open LSF, and then Platform LSF when it got bought. And some of the engineers worked with IBM for a while, and then they said, we're going to go back to that old version and we're going to fork it. So they forked it, and they either brought the code or they remembered the code or who knows what, but IBM sued the shit out of them, and now OpenLava is gone. So that's why I say feel free to read about that. It was pretty tragic. It's also one of the reasons I'm not a big fan of IBM. I've got a lot of reasons not like a lot of the bigger companies, but whenever somebody tells me, oh, IBM's a big fan of whatever, I'm like, I don't know that they support open source like you guys think. All right. Networking, most of these operate on at least 2 networks, but some of these nodes operate on 3. There's a management network, so your management node is controlling things and talking to things, and it's talking to your different nodes, and maybe it's even controlling the management portion of your storage system. But then all of this light blue is your InfiniBand network that only passes high-speed data. That's all it does. It is not interested in passing your notes about who's in charge of what. It doesn't do that kind of stuff. It only passes the data, and that's an important thing to know. Management, transfer, or login nodes, so management, transfer, and login, which I'm not showing here, they sometimes are allowed to connect out, and that's what we call an air gap. When only a couple of systems can get into your environment, everything else has no route out, that is considered an air gap system. Air gap to me is best shown with this right here. If any of you guys remember the old Magneto in a cage, that's how I think of an air gap system right here. That's an air gap system, right? Do you guys remember when he was hung out so he couldn't use his magnetic powers to fucking kill everybody? Couldn't just rip the walls off and stuff like he normally could, so they had to have him out on this glass and plastic thing. That's an air gap in my mind, right? There's only one way in and one way out. All right, get out of there. Did I close that other one? Oh, I didn't. Okay. Shared storage, right? So all of our cluster has a shared storage that can execute job slices against the same data set. Everything needs to see the same data. Then we use high-speed storage area networks to transport data only for compute functions. That's what I keep mentioning there. Lustre is an open-source distributed storage system that requires clients to register. Once you're registered and checked in, then you can just go check out the metadata servers and the metadata targets to find out where your data is, and then you go pull it directly from the object storage servers very quickly. It's a very fast transaction. You never have to go back to the management stuff again. You just go hit the object storage servers, and it makes for extremely fast file system reads against that system. So here's what Lustre looks like. Lustre was owned by Sun. Sun got bought by Oracle. Oracle said, what the fuck is this? And they chucked it back out to the open source community. So OpenSFS runs Lustre now. This is what Lustre looks like. This is a really good read if you want to spend a little time. But this is that process I was talking about. You've got some kind of high speed, typically InfiniBand. It can be Ethernet. It can be fiber channel over Ethernet. You can get tremendous speeds out of that. InfiniBand tends to be a little bit faster, though, if we're being honest. And then Omnipath. I've never used Omnipath, so I couldn't really speak to that. But the Lustre clients come in. They register to the management servers and get put into the metadata, the management target, and they get registered in as a, client for the system. Then they can go and check stuff out from any of these metadata targets and find where the data that they want is, where the individual blocks of the file system reside, over here on object storage targets. Then over super high speed links to these servers, these object storage servers, OSSs, they go and they communicate and they pull the individual blocks that they need down, and they can be pulling data from 64 different object storage servers. This is why it's so fast to recreate a file between the two of them. You can just be pulling, and you're not checking back here each time. You already pulled all the info. Now you're just shotgunning it across the network, and it's almost like a beer chug with like 64 beers. Your system, your client, it needs special kernel modules and clients that you build on these systems to be able to even communicate with this, right? Then there's fun stuff that goes on here. You've always got a primary link, so these are the primary links, and then you got backup links in this idea. If either of these stop listening, you always have a heartbeat running, and then you always have a connection to the other one's IPMI. And there's an old tool that used to be called Stomith, shoot the other motherfucker in the head, but now they call it for, PC and being more acceptable to the general public, it's called Stoneth, which is shoot the other node in the head. If this system detects that this system is not properly sharing that at the correct speed, it is not responding, it's got processes wrong, it kills it via an IPMI kill. It shuts the box down and it takes over its storage. That's what it does. We're both walking along, we're carrying our loads, and it's whatever, and I look over and you're struggling, I just shoot you in the head. That's what the Stoneth stands for. Shoot the other node in the head, take the load, keep walking. When that one comes back up, you can have fail over and what we call fail back. Most of us do not ever turn fail back on, because what if this goes into a boot loop? We don't want to do that. We always manually fail these back. That's my advice as a guy who managed that for 5 years. And then they talk a little bit about the pieces and how it works, what major minimum components you need for this to run. All those components I just talked about right there. Fun things about this: if the MGT goes dark, you still have a fully functioning Lustre cluster. The only thing you can't do is register new clients in. So that's one of the reasons this is tremendously useful. Once your clients are in, you can keep going to the metadata target and keep writing or reading files out of the system. Very, very, very fast. And it's been worked on for a long time. There were 3 different open source projects, and then they got together and started OpenSFS. If you guys want to look that up, here's the OpenSFS page. And they do a Lustre Con every year, or whatever they call it. I think it's mostly in Europe. But Lustre tends to be in the top 500. It tends to be like over half of them. And it's probably, there was one point where it was 90% of the top 100. I don't know if that's still true, because I just heard the other day that Lustre's not represented in the top 20 anymore. That may be true, but it still comprises a huge amount. And you can feel free to go hit that top whatever site later and look at it. All right, GPFS, IBM proprietary distributed storage system, does all the other types of things that a big distributed file system would need. It's very mature in its space. You do have to have special, both of these require specialty clients to connect to. You do have to have the proper build and all that kind of stuff. One of the things we do in the high performance compute space is we build matrices of all the versions of stuff that we're on. So, what version of the OFED drivers are we on? What version of the Mellanox drivers are we on? What version of GPFS are we running on the ESS side, so on the actual storage side, and then what are we running on the client side? And as we move into new versions and we get new drops, we call them drops of new equipment. As we get new drops of new equipment, we need to make sure that matrix is updated, where the new stuff's going to come in on like the newest stuff, and the old stuff we need to make sure is at least updated to a version that can still handle whatever the storage is going to. So there's all kinds of things to consider in this space. All right, GPFS, we go over here and you walk through. There's some talk about it, and there's some images here and stuff. It's IBM proprietary again, so you're spending some money. And a lot of times where you pay in there is to have disks that are updatable. When you buy proprietary file systems, sometimes you get the proprietary file system for pretty cheap, but the disk and the disk firmware can be up to 3 times the cost of a normal disk. And it can be wild how expensive that stuff can get, but it works. It's got really good rebalance. I really like their rebalance, security, and other functionality. What rebalance is I was talking about this earlier. Let's say you have 5 petabytes over here and 5 petabytes over here. That's not even big nowadays, but let's just say. And this 5 petabytes is all your old stuff. And you add 5 petabytes of more disk, right? So now, and you've got more channel controllers, and you've got all this stuff, kind of like how NetApp is, exactly how NetApp is. In fact, it's not that cheap to get it, but to use the disks and stuff can be really pricey. So anyways, 5 petabytes here, old, all the data that your company's run for the last 10 years. And you add 5 more petabytes. You got more channels, so you get more speed if you're writing over here. But I just want to think about this real quick. Now you start getting new data in. You're doing data sets that are like 200 gigs. So all of them start getting written over here. They start going over here. So this 5 petabytes is all your old data. This is all your new data over here. Well, what's going to happen when old jobs have to run? Everything's going to go over here. Over here. And then when new stuff gets written, it's all going to go over here. That's not super efficient. What we want to do, once we stand up new, so we've got the old 5 petabytes and the new 5 petabytes, we immediately begin rebalancing. And what rebalancing is I'll just start writing blocks over here. And I'll kind of slide it all down to where now my data that was, from the last 10 years is across all of this. So now reads and writes, primarily reads from old data, is going across everything. And writes of new data is also going everywhere. So now I get all that speed increase, right? You general host Windows, right? Netstat A terminal show established connection. Very interesting. Okay, we're not going to do that, but we're going to keep working on this stuff. Okay, air gap tooling. So I said most HPC systems are kind of slack in their application of patching and system security. It's common to work in a system that hasn't been patched in many years. One of the safeguards for this is an air-gapped network. So we have it gapped off where the only things that can communicate are going to be our the stuff, the only things that can communicate in are things that are out to other networks, okay? Only the following systems have their own connections out. Typically, like login nodes, we allow users to connect. They can become, management if they have administrative credentials. We allow the administrators to connect. Typically, they have to come in through the logins nodes first. We don't want them to just be able to connect from anywhere. And then we've got transfer nodes that allow high-speed dedicated connections to move data out. So those transfer nodes will have, they'll have, you can run SFTP on them, or maybe they've got high-speed transfer out to external systems where maybe we need to move data sets or process things out to, okay? HPC tooling. So this is stuff that I've worked with a lot as far as supporting it, but I don't know much about it. But I'm going to tell you that there's some really cool applications out there for BioPerl, BioPython. I've never seen these two used, BioGo or BioRust, but BioPerl is a very well-established, didn't sound like air-gapped. Okay, so BioPerl is one for doing multiple, all right, and for doing Perl, and then BioPython is one for doing Python and those things. And I tried to find, they have their tutorials, but they used to have a place where you could just go in and execute and see how some of this different stuff worked. All right. So anyways, then we got BioGo, BioRust, if people are into some of these newer, more modern things. They got, these don't look like these are as developed, but they're more wrappers and libraries for people that are doing more modern type of stuff. I figure some of you guys that write more code care about this stuff. I mostly support this from the under the hood type side of things, right? All right. Anyways, and then this is a big one. This one's like what I was mentioning earlier about like different companies and different countries actually reach in and pull data out of like NOAA. This is NOAA's project for it, short range weather applications, right? And they've got their development branch. They've got a bunch of stuff you can look at. You can go look at releases of data that they put out there and what they're working on and all that kind of stuff. So if you want to go get involved with this as a user and you want to see how to use their short range weather app, they have it all out there, right? And this is a downstream from high performance compute NOAA weather environment. And then other people use that and do more production work on that to answer questions around all kinds of what's going on in the weather and that kind of stuff. Let me point out too, and I have a client that does this. They pull data from NOAA, they add value to it, and then they sell it. They make money off of that. There are. All right. But again, these kind of things when we're talking weather, it's very critical that again everything we do in HPC can be done on one computer if we wanted to. You can do it on one computer. Problem is, it's going to take 4 weeks to get to, and this weather stuff tends to be churned every 6 hours. So NOAA produces weather every 6 hours, and sometimes faster. But it's definitely distributed every 6 hours so that everybody else can kind of keep up with what the predictions are and that kind of stuff, right? And there's all kinds of work in that space. Other types of tooling that you're going to kind of see, and if you're a sysadmin and systems engineer, you don't need to work necessarily or care about what PyTorch or TensorFlow are doing. You may know that from machine learning and some of those type of tools. But you're going to see that, and you're going to get those kind of things kicking off workflows in your environment. So it's sometimes useful to understand what they're doing and what some of the common libraries are, right? That kind of stuff. Some of the clusters I work with, we have dedicated resource nodes that do allow connections in, and then these users can do tools for building projects right in the cluster. This tends to be, so like Jupyter Notebooks is going to be Python typically, right? It's right in the name. Jupyter Notebooks, and again, I made this generalization when I talked to the Linux group earlier. Hopefully, this doesn't hurt anybody's feelings, but Jupyter's notebooks tends to be, in my mind, the more junior and the like lower, like the newer researchers, newer scientists, newer engineers. In my from my experience, the R Studio tends to be people who have been doing it longer. They care more about the statistics and the math, and really the only difference is Python users and R users. It's just that's been my observation that like the R Studio users are more of the I want to say just like the older, more experienced ones, but that's not 100% true. I'm just saying that's a generalization that you might see things. So you may get questions from the Jupyter Notebooks users that you're like, really? Like they're having a problem with that thing? And you won't see that as much with the R Studio users. I almost feel like these ones only come to me when they really, really need something, and there's really something wrong in the space. So something to think about there. Yeah, data science with R is big. Plus R is stats. Like I have friends that do economics, and they've never heard of Jupyter Notebooks, but they use R all the time, right? They do production type, all that stuff. All right. HPC monitoring, right? So monitoring of any system is always critical, and if you're going to be a Linux engineer of any type, you got to think about your monitoring. We have a whole separate talk on telemetry data, right? Data to distance, logging data, and then trace data, and what those three things mean. One of our engineers that shows up pretty often, Data Sherpa, he wrote up a couple of Medium blog posts. I think Medium is what it's called. I don't know. But he posts them up in the Discord, so if people like that stuff. Python's very dominant. That's for sure right now, especially with like I'm an amateur data scientist, and I play around. You guys can't see my screen down here, but I play with like it's covered by the little thing. It's not on purpose. It's just my little tickers over it. I have idle like Spider, and I like Spider Python because it kind of gives me. I can see the visual and I can see the output, and I can do my little data science playing around with stuff, right? But I'm like a very amateur data scientist type guy. I don't do that professionally. I just do that for fun. And Python's by far the easiest thing I've found to get into that. So I think that they've probably found that like it's a short ramp up to doing useful things. Whereas like I think with R, like not everybody that goes to university is going to be a serious coder their whole life. Some of them are just trying to take those classes and get out, right? And then they're going to go on to do other things. So that's my thoughts on it. Let's talk about logging. The one that's been around forever in Linux world is rsyslog. Syslog, but rsyslog is kind of what's sitting there. It aggregates all the logs to one or two systems in the cluster. Then there are other tools that can do logging, but in that Shasta system, man, it was novel. I loved how Kafka worked there. We would just everything just sent into the Kafka bus. And the Kafka bus is just sitting there. It's kind of like how Event Bus or Event Bridge works in AWS, right? So logging can be sent directly into Kafka bus for critical or incident level. On the other side, it's all getting pulled out into Elasticsearch and being shown by Kibana. And that was a really awesome way that Shasta did it. But again, like Shasta just kind of, Cray got bought by HPE, and HPCM's their flagship. So I don't suspect any of you will ever work with Shasta, but I still included it with this because it had so many cool things that were going on. Monitoring has changed a lot over the years. I should add Cacti to this too. I know one of the last guys that's still supporting Cacti, but monitoring, a lot of older monitoring was done by SNMP. That's just the way we used to do it. SNMP version 2C and anything lower than version 2C of SNMP should not be used. It's not considered secure. Modern monitoring is more robust, but let's talk about the way that a lot of it used to be done. Ganglia and Nagios were big. RRD tool and Cacti were also real big too. I should include those. But they heavily relied on SNMP. The SNMP, by the way, is simple network monitoring protocol, right? And what would happen is your node, like let's say I was a computer node, I would kind of write a little message here, and I would just kind of like put it on like a little wall. And you can SNMP walk my wall for MIBs, their message, I forget what MIB stands for, and OIDs, and you could scan, and they were always in this hierarchy, this tremendously long, ugly hierarchy of numbers that is not meant for you to know, but your system can scan it real quick. And we could look for it would be presenting like, hey, this service is on or this service is off, or I'm using IPv4 with a certain flag set that isn't really good for TCP, and there were all these things that you could scan. My problem with SNMP is this, and anybody that's used these systems know this. That SNMP process that was doing this, whatever this message is, it's dumb. It's if your system locks up or you're doing something that's causing the box to be under tremendous load, this doesn't get updated anymore. And what happens is you say, well, hold on, if I got a timeout after 3 tries, no, I didn't say that it wasn't still showing. I said it wasn't getting updated. Do you see the problem there? I'm still holding this little thing and I've got little derpy eyes because I'm not updating things, but what I'm presenting to the system is not accurate anymore. That is one of the major problems with SNMP. Is it's a poll, POLL. I'm polling you for data. Your data is not accurate because you're frozen up, and that's a major problem with it, right? Visualizations were built into these tools though. So like I actually have, like, not everybody notices this. When I pull Ranger Cam up, I don't know if you guys ever see, I got Nagios at the bottom here. I'm running Nagios in my environment because I've been using Nagios for like 20 something years. So I have Nagios up in my environment, right? But it's I got some nodes down and other stuff, but this is just a web frame pass through on a old Grafana page. Oh man, some of my boxes are down, right? But I can see what's going on in my environment. I don't know if any of you have thought about that, but how do we do, what's a more modern way of monitoring things? Like Grafana's, Grafana is the way, but you'll notice almost all of my monitoring that I do is in Grafana. But nowadays, what we do is we do a lot more of tools are arranged into a tool chain, and they specialize in just one part. So the old beats, there was a bunch of them. There was metric beat and file beat, and I think like service beat, and there were probably 100 of them if I were to guess. Those things can push data into all kinds of different things. They could push it directly into Elasticsearch. So they used to be part of what was called the ELK stack, Elasticsearch, Logstash, and Kibana. You would have beats on the server, and the beats would be pushing data off. So it's a push model. They only push data when it's updated, or when they can, right? Telegraph is one I really love. Telegraph works with all kinds of stuff, but they send system level alerts maybe to Kafka, maybe to InfluxDB like I use in my home lab, maybe to Prometheus. These can both. I don't know if Beats can send to Prometheus, but I know Telegraph can. And then that gets aggregated up maybe to Elasticsearch or simply to Grafana, right? Grafana can pull that out and then shown by Kibana. The model that I'm showing right here, though, Beats to Kafka to Elasticsearch to Kibana, that is exactly how Shasta tried to do it. And Shasta was excellent in its alerting. But each of those things, when you think about them, are not the older tools, they were the full solution. They did SNMP, they did the user login, they did the showing you the data. Excuse me, they did everything. Nowadays, it's a lot of open source projects, and you're arranging them into a tool chain, and you're hoping that it's all stable, right? So anyways, this means you have to know more about all kinds of things, right? And we don't always want that as engineers, like to have to know a lot of stuff. We want to specialize sometimes. It just depends, but more stuff to keep in your head. All right, so here's our review. We talked about what HPC is, and for the purposes of this discussion, what it wasn't. We talked about how it's used, what industries are out there, system skills you need to bring to the table, right? I assume that, and I originally did this for the Professional Linux Users Group today, but I'm also talking to you guys, people that watch me probably care about doing some Linux, at least as a hobbyist. If you want to make this a professional career, you need to kind of tune some of these up and get a little better as maybe at some of these things. If you don't know them, you want to. And then we talked about all the HPC individual components, right? And there's a lot there, so we just really kind of touched over the top. Where do you go from here? Build your skills in Linux. That's always valuable. I don't think there's anything lost learning how to use the command line, right? Like getting in the command line and doing these things are just, I think they're just valuable, right? Understanding how to do these things is important. Build your skills in HPC where you can. There's a lot of open source tools. As Fisherman mentioned earlier, you could just take a 2-node cluster, set up XCAT on one node, make him the main or the master, make the other one the worker, and then you can set up Slurm control daemon over here, Slurm D over here, Munge D on both with its little shared certificate that you do, and all your stuff could start working. You could start scheduling jobs to that one node from this node. Actually, you can schedule jobs to itself too if you wanted to. So Slurm D could be running on both, and you could have a high performance compute cluster with just those two little nodes. Would it have? And by the way, in my cluster, I'm gonna have that shared storage, but it's gonna be NFS. So like I keep telling you guys, we can dress it up as much as we want. It's still not going to be very fast, right? It's gonna act like everything that an HPC would do, but it's not going to be an HPC, right? And then with my limited knowledge and what I've been able to do before with bioinformatics, we could pull up, we can go get some FastQ or FastX gene sequences, and we could run against them and watch processing and stuff with some of those libraries if we want to. We will have an HPC environment by the end of August. I did that because I'm not gonna time commit to like only a couple weeks. For you guys that have been here, I don't have it up right now. My Excalidraw has that included up here, and this is our kind of what we have in here. So I got 90 gigs of RAM, 1.4 terabytes. I got about 32 CPU cores. I could run more than that on the CPU cores, but I don't want to lose anything. Ceph have much use. You know what? Ceph's an interesting thing. So I've never seen Ceph in HPC. I saw Ceph in some big data for like AAA back in the day. But what I saw with Ceph was it got picked up by Red Hat. And then I mainly see it being their like big distributed back end for their OpenShift. That's what I mainly have seen it for. I've never, unfortunately, seen it used in anything like that. Yeah, I figured you meant HPC. I read it as HPC. No, but I've never seen it in like a government or that. It's probably sneaking in there nowadays. It's probably there. But I haven't seen it there. I've mostly seen it ever since Red Hat picked it up. I want to say they picked it up in 2018 or 2019, because I seem to recall when it came around with OpenShift. And then it's still kind of like their preferred backend on OpenShift, because they picked that up in Gluster right back. And I love Gluster. I think Gluster is an excellent tool. By the way, guys, Gluster has nothing to do with Lustre. They're two totally different tools. But they are both based on file systems, and that's about where it ends. But Gluster is an awesome tool that was also picked up by Red Hat, but I feel like Red Hat didn't really, that's kind of like its stepchild. It's not recommended to be used in OpenShift and any of that kind of stuff. Limited power computing, interesting. All right, so where are we at? So then where else do you go? There's government programs that are out there. So I put these, by the way, these are all up in our Discord. So if anybody wants, on our Discord, I have this chat in our presentation section. And we talked about, different things, other stuff you can go look at, more stuff you could read about. There's a NIST standard for HPC security. I'm telling you, HPC security is not the best. It's not the best as far as security goes. But they have it right here, and they talk about how your cluster should be set up and those kind of things. Okay. And then questions. Yeah, if you got questions, drop them in Discord. I hear the wife downstairs, so I got to get off of here soon. But yeah, let me know if you guys have any questions. This was our main topic today, was learn about HPC and how to get the skills in that area of engineering. If you guys are going to work on that stuff, or if you need help with that, the Discord's always there for people to get better. And the goal of that, again, the stated goal of the Professional Linux Users Group is to take this from being a hobby to being a career, right? Like, we're all hobbyists here. Everybody here, like, we have our fun, but yeah, I appreciate that, Creedite. And I was thinking about it. I do need to better explain that it's an air-gapped system, but they're bastion hosts to get in. So I do need to explain that better, because as you were mentioning that is, you are air-gapped if you're completely off the network, but there are bastion servers that can get to you. So I need to do that. So, yeah. So, yeah, it depends. The ones that I've seen, you typically have to jump in from like certain systems. But yeah, no, I appreciate you guys all coming. And yeah, easier for work from home. Yeah. And I'll do more demos too. We did a little more demo in the Prolog group than I did today for this, but I definitely appreciate you guys all coming by. Let me see if I can find. Let's see somebody to raid. Let's see what's going on out there in the world. Who's doing tech stuff? Don't see anybody doing tech. Well, I guess I can go look for somebody doing tech. Give me a second, real quick, guys. Go to Twitch. Let's find somebody in science and
gravityless
technology. Let's go find somebody to raid. Nerduino. Did any of you guys know Nerduino? Yeah, we'll raid him. He looks like he's doing something fun.
So in addition to...
So I'm going to raid him, and I appreciate you guys all coming. Let's see. I will see you guys. I'll be on tomorrow. We're doing all Linux labs tomorrow. It's all Linux stuff. So I will see you guys later. Thanks for coming by. Get our raid on.
I've got like 8 patches here that we can give away as well. They're all sort of prototypes.